The broadcast is now starting. All attendees are in listen-only mode.
Welcome to ASWA's webinar. My name is Deirdre Mason. I am with the Association of State Drinking Water Administrators. And for our webinar today, we are going to be talking about PFAS, analytical methods, application, comparison, and lab accreditation. So for those of you who don't know about ASWA, our mission is to protect public health and the economy through the provision of safe drinking water. Our members are the Drinking Water Program administrators from the 50 states, territories, the Navajo Nation, and the District of Columbia. And they provide public water system oversight in the form of regulation, technical assistance, and funding, and coordinate with multiple partners. We have two PFAS webinars that we're putting on this month. Today's webinar is on analytical methods, and our webinar next Wednesday is on PFAS treatment options and considerations for drinking water utilities. So we hope you'll be able to join us for next week's webinar as well. So the purpose for today's webinar is to provide state and territorial drinking water programs with an understanding of analytical methods and to help them provide assistance and recommendations to the water systems in their state. The primary audience for today's webinar is ASWA's members, the state and territorial drinking water program personnel, but we've also invited state association personnel as well as EPA and federal water colleagues. So I just want to remind you that because it is for our members, we ask that you, the other people in the audience, please limit your questions so that they can be able to ask them first. And today's webinar presenters come from New Hampshire's Department of Environmental Services. We have Brandon Kernan from the Association of Public Health Laboratories. We have Sarah Wright. And from EPA's Office of Research and Development, we have Chris Impellitteri and William Litz from Eurofins Eaton Analytical. And from DOD's Laboratory Quality and Accreditation Office, we have Janice Willey. So just a few housekeeping items. We will have a video recording of today's webinar on ASWA's website within the next few days. And we ask that you please type your questions into the box on your webinar control panel. We will not be taking any verbal questions, and you may type your questions into the box at any time during the webinar, and we will wait to answer all the questions after the presenters are finished speaking. So with that, I'm going to go ahead and hand it over to Brandon Kernan, who is our first presenter. And Brandon is the manager of the Hydrology and Conservation Program at the New Hampshire Department of Environmental Services. Brandon?
Thank you. Today I'm going to go over New Hampshire's experience with sampling PFAS, as well as go over a primer that ASWA has developed. We have a PFAS work group that we've developed that provides guidance to state drinking water programs and also water systems on how to assess PFAS. Excuse me. So first of all, I just want to give a little bit of background on PFAS regulation in New Hampshire, so you can see the importance of sampling and analyzing for it. And first of all, our state has adopted an enforceable standard. It's an ambient groundwater quality standard, which is used for cleanup at waste sites. But in New Hampshire, that's also an enforceable drinking water system for regulated public water systems. Our standard is based on health criteria only at this time. However, our state recently enacted a law that requires my agency to initiate rulemaking to develop maximum contaminant levels for PFAS compounds, PFOA, PFOS, and PFNA, and PFHXS by the first of this year. So we have to start the rulemaking. And in that statute, we must consider the health benefits of the MCL as well as the cost and technical feasibility of implementing it. Our state also has a law that's been passed recently that requires my agency to develop a plan for developing a surface water quality standard and a budget for developing that by January 1st of 2020. We also recently had a law enacted in our state that gives us clear authority to regulate air emissions to ensure that groundwater quality standards or NCLs that we adopt are not violated. So we've been sampling for PFAS for several years in New Hampshire. Like all other states, we were involved with the unregulated contaminant monitoring rule starting in 2013, where the very large water systems and a few small water systems had a sample for a list of contaminants established by EPA. And so at that time, we had 21 water systems and about 80 water sources tested for PFAS compounds. The reporting limits under that program were 20 and 40 parts per trillion for PFOA and PFOS. And although that seems high in today's terms, at the time that was considered very low at part per trillion levels. After that, the Department of Defense started implementing PFAS sampling at Superfund sites, and we found impacts at the former Pease Air Force Base and had 3 major water supply wells impacted, one of them over the current standard of 70 parts per trillion that we've adopted in New Hampshire, or it's also EPA's health advisory. In 2016, we became aware of the potential for air emissions causing groundwater and surface water contamination at a couple of facilities in New Hampshire that manufactured coated textiles, and we became aware of that because of sites in New York and Vermont that had similar activities. And from 2016 on, we've been broadly sampling for PFAS in the state. In 2016 alone, we sampled about 1,000 private wells in response to a couple of those air emission sites that we were determined to be contaminating private and public water supply wells. And since 2016, we've now collected over 3,000 samples, and it's gone beyond just drinking water. It's also been waste site, groundwater sampling, wastewater, biosolids, soils. There's even been fish sampling that's been conducted in the state. Our agency has integrated sampling for and regulating PFAS throughout its various regulatory programs, and this pie just shows all the different areas of my agency that are impacted. Groundwater at wastewater discharge sites, that's where entities don't have access to a river to discharge their treated wastewater, so they discharge it to groundwater. We have sampling ongoing there. We've done targeted sampling near land uses that we thought could be impacting nearby wells. We've done some statewide surface water sampling as well as surface water sampling at contaminated sites. PFAS sampling has been integrated into our existing contaminated site water quality monitoring schedules. We're requiring new sources of water for any type of public water system to sample for PFAS. We're sampling at sites with air emissions that are believed to have PFAS associated with them. And at this time, we've had a voluntary public water system sampling program for PFAS as well as a targeted one. And soon when we adopt the MCL, PFAS will be part of regular monitoring, the regular monitoring program for public water system. This is just a map that broadly summarizes a lot of the sampling data that we've collected in the state. And you'll see we have detects all over the state, and we have contamination sites that were already pre-existing that have found to also have PFAS. They pre-existed because of other contaminants, but when they sampled for PFAS, they detected it. And it's my belief, based on my understanding of the different detections we're seeing throughout our state, that this isn't really any state in the nation. If your state that you're in implemented broad sampling, you would find the same type of detections near the same type of land uses that we have in New Hampshire. And just on our website, we have a PFAS webpage. If you go to Department of Environmental Services homepage, you'll see right on the top of our page a link to our PFAS information. And a lot of our sampling data is reported right into our database and presented on a viewer that's sort of in a Google Earth environment where residents can type in an address and see data nearby. And so if you're interested in looking at more occurrence data, I encourage you to do it. And the results are broken down into supply wells, surface water, and other types of samples. Just to give you a summary of some of the results we've had from our public water system sampling, we broke it out by concentration here, and What's really telling is that when you start looking for PFAS, and this table is showing just combined PFOA and PFOS, we start looking for it down below 10 parts per trillion, a level that some toxicologists suggest it should be regulated at. You start seeing pretty high occurrence data. To have almost 10% occurrence over those levels of a man-made contaminant is pretty unusual, and if regulated at that level, could have huge cost implications, especially if you extrapolated this out to the 3,000 plus sources of water that New Hampshire has a public water system. Never mind the 250,000 private wells that potentially could be impacted by this as well. Just to give you a sense of its occurrence by different types of sites, we have a summary table here that shows in the top row are existing waste sites. Again, they existed because of other regulated contaminants, but when they tested for PFAS, we see about 54% of them exceed our standard for PFOA and PFOS. And then going down, you'll see other land use activities such as auto salvage yards, landfills, and fire departments as being areas where we find elevated levels of PFAS and PFOA and PFOS in the groundwater. We've also sampled about a dozen wastewater plants just to get some background information, and you'll see you detect PFAS in all wastewater, including the phased out or banned PFOA and PFOS compounds, as well as the newer compounds that are in use. We've also done broad surface water sampling, both just general surveillance to look at general PFAS occurrence in surface water, as well as more targeted sampling. You'll see on this map, we have higher hits in some areas, and sometimes it's just a stream that's not near anything specific, but more often it's streams near landfills or fire training areas where you see these elevated levels of PFOA and PFOS in this slide. Now I just want to go over the primer that ASRA was recently developed, again, to assist state drinking water programs with providing guidance on how to sample for PFAS, and also can be used as guidance for water systems. And this primer, again, was established by the ASRA work group on PFAS, and what we attempted to address in this is to provide some basic sampling protocols, identify issues that should be considered by a state or a drinking water system. We also try to show some decision points where you have options as a state or a public water system on how to go about sampling for PFAS. We try to identify some potential problems, as well as some context of how to interpret results if you do sampling. So one of the first topics that we address in the primer is identifying an analytical method, and I think the later speakers are going to probably get into some more detail. But basically, you have two options at this time. It's EPA's method 537 or isotope dilution. Both methods are good. Both have some pros and cons. The EPA method 537 is a method established by EPA originally for UCMR3, but it's been continued to be used by commercial and state laboratories. It's the only common method used at this time by labs, so it's the one method that you can go from lab to lab and they're all measuring PFAS in the same way. The method is a little more cost-effective than isotope dilution, but some of the downsides of it is that it only includes 14 analytes. It's not really intended for non-drinking water samples, and that method doesn't include corrections for matrix interference. Isotope dilution is the other option. This option is actually considered to be sort of the gold standard by many chemists. It can be applied to non-drinking water samples. It can include more analysis than method 530, more analytes than method 537, and it allows for corrections for matrix interference. Some of the downsides to this method is it's more costly, and at this time, and that's sort of quote unquote this time, is there are new methods being developed. Labs are using their own proprietary method when using isotope dilution. So the method one lab uses to measure PFAS via isotope dilution isn't exactly the same as that of another lab. Another topic we addressed in the primer is if you are a state drinking water program or water system, how do you go about finding a qualified laboratory? And we provide guidance on how to look up labs that are accredited with either the National Environmental Laboratory Accreditation Program or the Department of Defense. And so we provide links to websites and sort of some guidelines on how to identify the analytes in their analysis query. I'll also note that some states have their own accreditation or certification program, and that would be a good resource as well to see what labs are qualified to analyze for PFAS. There's some other things you can also do to make sure you're working with a qualified laboratory. First of all, you can work with multiple labs and do split samples to make sure you get similar results from lab to lab. In my state, in addition to making sure we use accredited labs, we've done double-blind proficiency testing where we've had samples prepared of a known concentration and sent them to labs to see how accurate and precise they were. And then you can also ask for historic proficiency testing data from laboratories. So the third topic we address in the primer is what chemicals should be analyzed. Again, method 537 has up to 14 analytes, but that doesn't mean the labs all offer that many analytes when they provide method 537 services. Isotopic dilution can include up to 30 compounds, and many labs have different testing schedules and have longer and shorter lists of analytes that you can choose from. In the primer, we recommend that 6 PFAS compounds be analyzed, and we reference the compounds that were included in the UCMR 3 program. EPA identified those as being important based on likelihood of them occurring in the environment and potential concern for toxicity. Also, based on the occurrence data that states observe from their PFAS sampling, we recommend that 3 other compounds be included in the testing, just based on the fact that they're being found in the environment. But you go ahead and analyze for these as well to capture as much information as you can. The benefits of using methods with an extended list of analytes include getting as much information as you can when you sample. It takes time and money to go out and get the sample, and why constrain the analysis and limit the analytes when it only costs a little bit more money to include more analytes. Having a longer list of analytes assists with fingerprinting or segregating potential sources of contamination. Different sources will have different PFAS associated with them. Also, the science continues to emerge on health studies, and you may need this information later as new toxicity information is developed. And then lastly, some states are developing health guidelines using an additive approach, summing up a longer list of compounds, such as 5 PFAS analytes, so having this information could be important. The downsides of having a long list of analytes is that it might cost a little more, you might have the text for something that you don't have health guidance for, and of course, it would be more processing of the data. I just want to point out when we talk about what you should analyze for, we have noticed that commercial labs are referring to the PFAS analytes in an inconsistent way. Some are listing the salt form of a PFAS analyte, and some are listing the acid form, and they're not interchangeable necessarily, even though the acronym is the same. They're not the same chemical, and so because EPA's health guidelines are based on the PFAS in the acid form, and in my state it's the same, we're requiring labs to report the data in the acid form and really ensure up front that they get the nomenclature of the compound right and the appropriate CAS number correct. That way, as you get data in from different labs, you will have just one set of analytes for each compound, opposed to having 3 different ways of reporting PFOA or PFOX. If you don't get that straight up front, it just creates havoc in data management, and you might have to make corrections to some of the data based on converting your result from the salt to the acid. And so that's important to work out with your lab before you start sampling. As far as reporting limits, certainly reporting limits have been lowered substantially over the year for PFAS analysis. The primer recommends that reporting limits of at least 2 to 4 nanograms per liter be utilized. Many labs using isotope dilution get much lower, and at method 537, labs are reporting between 2.9 and 14 parts per trillion. The benefits of lower reporting limits is that you can track trends over time, concentration trends, opposed to having a lot of non-detect data. You, again, can help fingerprint sources of contamination. And if you have a regulatory standard or advisory value based on an additive formula, you would have these lower levels detected and added into the results. Primer also addresses things that might cause variability in the testing results. One of the first things is linear and branched isomers. Prior to December 2016, it wasn't clear in Method 537 if labs should or should not be reporting the branched isomer of PFOA. Some labs did, some did not. This is important because PFOA manufactured by 3M contains 30% branched isomers, and so if the lab didn't look for that, your result could be 30% low if your contamination of PFOA came from 3M. Some PFOA doesn't have branched isomers though, and PFOA made by DuPont contained only linear isomers. Another thing that can affect variability is that there's just there's a range of error associated with the analysis. At the lower reporting limits, the results are expected to be plus or minus 50%, and that's based on some testing, proficiency testing work that we coordinated with EPA a year ago. Under the UCMR3, the accuracy was plus or minus 30%, but now we're working with lower reporting limits, so that has broadened. Our work in New Hampshire has shown that we're usually accurate within 20%, but that's almost biased in the low direction. We have done a lot of split sampling testing in New Hampshire, and it shows that the different commercial labs reported very similar results for the same sample, and that we also split the samples to labs and had them analyzed using both method 537 isotope dilution, and both reported similar results. All these samples were drinking water, so pretty clean matrix. We did have the occasional blip of over-reporting or under-reporting. Another issue that causes some variability in testing results is standards. First of all, labs are trying to measure branched isomers of some of these PFAS compounds, but the standards that are available to the labs don't have branched isomers, so they're using the linear isomer part of the standard to estimate the branched isomer. Some labs also interpret branched isomer chromatographs differently because the peaks aren't as pronounced for the branched, and so where you start and end the integration varies. We also have worked with one lab to see where certified standards from different vendors were off by as much as 20% from one another. So right out of the box, you had variability just from the standards that the lab was using. The primer also addresses some sample collection procedures. It's our experience that water system sampling agents and operators are qualified to sample for PFAS. There's a little bit of extra care that has to be applied to the sampling process, and we just provide some guidance on the types of clothing that should be worn, the gloves that should be worn, and some of the things to avoid that you might have with you when you're sampling, like those traditional weatherproof field books that might be coated in PFAS. We also talk about the use of field blanks and trip blanks to make sure the sampling process and the shipping of the samples is introducing contamination. And lastly, the primer deals with how to interpret results. We provide references to EPA's health advisory, as well as the Interstate Technology and Regulatory Council's table of state standards, guidance, and advisory levels. And actually, that table has values for other countries as well. We also explain in the primer that the detection of low levels of PFAS doesn't mean there's a major source of contamination, that there could be contamination from within the plumbing system. There's a lot of fluorinated components in the plumbing system that could be sources of very low levels of PFAS. Even some of the chemical feed tanks and tubing are known to be made of Teflon because of their chemical resistance, and the impact of that on low levels in water is not really understood, but because it's there, it's a potential source. And also, it's just other regional and more diffuse sources of PFAS that could be causing low levels. It's important, though, that you have appropriate number of lab blanks, strip blanks, and field blanks, and duplicates to make sure you know what you're dealing with when you have low-level detections, if it's real or if it's some other source that's not actually in the drinking water. All right, thank you.
Thank you very much, Brandon. And our next presenter is Sarah Wright, and she is the Environmental Laboratories Manager for the Association of Public Health Laboratories, excuse me.
Great. Thanks, Deirdre. Can you hear me okay?
Yes.
Great. Well, hello, everybody. So in my role as Environmental Laboratories Manager, I help to strengthen state and local public health and environmental laboratories and liaise between them and federal partners. And I just wanted to give you all a sampling of a few labs that are doing PFAS testing. So first, with the Minnesota Department of Health Public Health Laboratory, they started doing groundwater testing in 2003 in an area east of the Twin Cities Metro. It was suspected that it may have been contaminated by a large PFAS manufacturer. In 2007, they added biomonitoring and performed 3 rounds of testing on citizens living in the affected areas. The purpose of that testing was to determine body burden and to assess groundwater treatment effectiveness. The matrices that they've been testing for over the past 15 years include drinking groundwater, landfill leachate, the serum I mentioned, and then also they've been doing a few different studies, one on dust and soil and produce. So they have a wide variety of matrices that they've been able to analyze for. And the public health impact that they've had with this testing, they've been able to perform, the state has been able to perform interventions based upon that lab data. So they were able to justify that the public water system should be filtered, and that they should add public water system connections or treatment system to the homes with wells, and then also verified that those were working. In 2010, the state of Minnesota sued the alleged responsible party for natural resource damages, and then recently in winter 2018, that lawsuit was settled out of court for more than $800 million. Over in California at the EPA Department of Toxic Substances Control Laboratory in Berkeley, they've been testing PFAS for the past 10 years or so. The initiative for that was in 2006 when the California Environmental Contaminant Biomonitoring Program was established through legislation. And so their first PFAS matrix was serum. Other matrices that they've been analyzing within that time have been drinking, surface, ground, and wastewaters. And then they've been able to perform targeted and non-targeted analysis for some of those. Their current research includes investigating the association of tap water and resident exposure, and then they're applying for a grant right now to be able to analyze 1,000 maternal serums and correlate that with the public water system. And this is just 2 of the many studies that they've been doing over time. The New Jersey Department of Health Environmental and Chemical Laboratory Services, so they started their PFAS method development in 2014. It's helped the fact that they have had the health-based drinking water standards come out for PFOA and PFNA, and then the proposed one for PFAS. They've been doing matrices for drinking water, 14 analytes in drinking water, and then also 12 analytes in serum. And if they don't perform testing on a certain PFAS, then they do provide technical help to state and other states or academia on PFAS compounds and how to best go about that analytical approach. Just some general state public health or environmental laboratory considerations if you're going to work with them. So some public health laboratories do have aged LC-MS systems and may not be able to detect the low levels that are required for certain methods. Some states are issuing equipment update capital requests because of that. Another issue that we all know about is that there's a demand for testing, but there's no consistency in the methods and certifications, and so it makes it very challenging for the labs to go with certainty when taking this on. Of course, the lack of staff and resources, because PFAS are unregulated, many times public health laboratories can't have staff fully devoted to this work, but the work might be done by contract workers or visiting scholars, which can have an effect on the continuity of that testing within the lab. And then if you are going to work with the public health laboratory, make sure you have conversations between everybody involved early and often. This can help to determine data quality objectives based upon the proposed data usage and the required reporting levels, and that can all highly influence turnaround times and the practicality of getting what everybody needs. So that was just a quick snapshot of 3 labs that are kind of leading the field with PFAS testing. New York is another state that is doing quite well, and you'll hear a little bit about the method validation study that those labs are involved with EPA from Chris. So that's what I have.
Thank you very much, Sarah. And so, yes, our next presenter is Chris Impellitteri from who is the Associate National Program Director at EPA's Office of Research and Development. And
thank you very much.
Remind you to go ahead and type in your questions at any time. We're holding them to the end. And go ahead, Chris. Thanks.
My slides okay, Deirdre?
Yes, perfect.
Great. I need to recognize first off my co-leads in this cross-agency effort. I'm from the Office of Research and Development, and co-leading this effort are Shotzi Fitzjames in the Office of Land and Emergency Management and Cindy Caporal in EPA's Region 3. So I'll start out with drinking water, an update there. As was mentioned before, the standard flagship method is method 537. It covers 6 substances under the UCMR, but there's 8 additional PFAS not listed in the UCMR 3 that are covered by that method. It is for finished or treated drinking water samples only. As Brandon mentioned in the talk about New Hampshire, in many instances, 537 has been quote unquote modified, and if any modifications are done to 537 outside of what is allowed in the method itself, then it is no longer method 537. It is another method. Method 537 is currently being updated for the compounds to add the compounds that you see in the bullets there. Perhaps the most prominent one is Gen X. And so that is being targeted to undergo a multi-lab validation. That was completed, or was targeted to undergo a multi-lab validation. That was completed in September. There's a draft method revision undergoing a peer review during this month, and we hope to have the final published revised method out by the end of November of 2019. There's also a new method that we're working on for drinking water. It involves solid phase extraction and an internal standard, and it targets small compounds. So 537 generally, not always, but generally performs poorly for small short chain compounds such as PFBA. This new method is under development, and the Office of Water is targeting June 2019 for a draft method for public comment. Shifting now to non-drinking water aqueous samples. We're currently validating a method. It is SW846, which is a solid waste method, even though these are aqueous samples. That's draft method 8327. This method focuses very much on simplicity, robustness, and maximizing throughput for production lab use. It's a very simple method. It's a direct injection, so it really minimizes sample transfers, any contact with extractions or other equipment. It is a very direct way of getting your sample from the field into the instrument with a minimal contact with anything else involved. And we all know that contamination can be a big issue in analyzing for these compounds. We hope to find a balance among sensitivity, ease of implementation, and monitoring requirements for this method. The direct injection method, 8327, includes 24 PFAS analytes, including all the target analytes in method 537. There are commercially available standards both for the neat or native compounds as well as isotopically labeled compounds. It is based on an EPA Region 5 standard operating procedure out of the Chicago Regional Laboratory. It is very similar to the ASTM method D7979. There were 2 phases to the validation study. Phase 1 was internal lab validation with 6 EPA labs. That was completed in December. We're currently in phase 2, which is a 10 external lab validation. There was an initial demonstration of capability for those 10 labs, and based on that IDOC, 7 labs were included in the validation and 3 labs were not. Samples unknowns, 60 unknowns samples were shipped that include surface, ground, and wastewater matrices in August of 2018, and we are looking to get the draft method out for public comment in winter 2018. Currently, we are in that external validation and have 6 of the 7 initial data sets back from the labs. We have 1 outstanding and hope to get that in the next week. And lastly, for this particular method, we're targeting quantitation limits down around 10 nanograms per liter. In addition to method 8327, we're looking to validate a draft method 8328. This is a more complex method relative to direct injection. However, it will be most likely more robust for complex matrices such as wastewater and biosolids. It accounts for matrix effects. It's an isotope dilution method. It affords options to meet DoD requirements. We're working very closely with DoD, and you'll hear from Janice Willey later. That's our main contact there, to make sure that we provide a method that meets or can meet the requirements set out by DoD. This method could allow users to perform a deeper dive based on a screening type method, such as 8327, if a particular client or a particular user needs to do that deeper dive. Method 8328 includes the same 24 analytes as 8327, but it also adds Gen X. It is largely based on an SOP that meets the DoD Quality Systems Manual 5.1 Table B15 requirements. Many of these requirements in the draft method are optional for users that wish to use isotope dilution, but may not necessarily have to if they're at a non-DoD affiliated site. It includes surface, ground, wastewater, as well as solids, so soil, sediments, and biosolids. Target quantitation limit is 10 nanograms per liter. We hope people can go lower than that, but in all instances, those parameters really should be established in that laboratory with their own instrumentation. We also hope to build in flexibility with columns and elution schemes for the chromatography. We realize that technology is and will continue to change, so we want to make sure that any advancements in column chemistry can be included with the method. We have two internal lab validations started. That's going well. We hope to move to a 10 lab external validation study. We all recognize with an EPA that this process, especially for 8327, just simply moved too slow. We know how desperately needed these methods are. So we're exploring a collaborative effort with DoD to jumpstart the external laboratory validation. We'd like to target, and this may be overly optimistic, and it probably is, but we'd still like to target winter 2018 for a draft method. Lastly, I just want to mention some other methods that, particularly in ORD, in the Office of Research and Development, we're looking into. One is the total oxidizable precursor assay. That's a method where all of the precursors to PFAS are converted over to analytes that can be easily measured. And it may give us a method to at least assess or broadly assess what the total, if you will, PFAS level is in a particular sample. Another area that we're actively involved with is non-targeted analysis. This is using chromatography and mass spectrometry to identify peaks based on their mass to charge ratio. And we're also focusing on, hopefully in the very near future, developing tissue methods, particularly for fish. This is the contact list here for all of us. Please do not hesitate to call me or email me, I should say, first, and then I'll give you my phone number and you can call me anytime. Our doors are always open. If I can't answer your question, I guarantee you that I will find the person in EPA that can. And I will I'll pass the baton, Deirdre.
All right, thank you so much, Chris. Next up, we have William Lips, who is the Chief Science Officer at Eaton Analytical. And William, are you ready to go?
Yeah, can you hear me?
Yes.
Screen's up?
Yep.
Okay. This presentation will compare 3 published methods used for the analysis of PFAS in water samples. One of the methods is EPA 537, a solid phase extraction internal standard calibration, LCMSMS method. Another is ASTM D7979, mentioned previously. It's a methanol co-solvation external standard calibration, LCMSMS method. And then another one is a new ISO method. It's still in draft. It's a solid phase extraction isotope dilution, LCMSMS method. In addition, I'm going to look at some of the problems labs have with deciding which PFAS method to run and some of the issues that can occur or be aware of, or you need to be aware of when modifying a method. This is my commercial break. I'll just continue on. One of the main difficulties or difficult issues for the commercial laboratory with PFAS analysis is that there are no defined regulatory methods, no maximum contaminant levels, and no consistent list of analytes between states. Which method do you run? As a drinking water laboratory, it is our tendency to stick with EPA method 537. However, customers request additional compounds and lower detection limits than are listed at method 537. Adding new parameters or lowering detection limits requires modifying a drinking water method, something that is not normally done, and as mentioned earlier, it ceases to become method 537. Eurofins Eaton runs method 537 for all of its currently listed compounds. Any modifications that we make to this method are referred to as in-house methods and not method 537 modified. We don't traditionally use ISO methods in the United States. ISO methods do not contain the QC criteria required by most U.S. regulatory or state regulatory programs. Obviously, EPA method 537 and ASTM D7979 do include the required QC. For drinking water testing, using EPA method 537 is the only choice. For additional parameters, you can modify method 537, as mentioned earlier, but what does that mean? You can create an in-house method, or you can run the ASTM method or its SW846 twin 8327 mentioned earlier. Now I'm going to compare these methods. EPA method 537 is a UCMR3 method validated by EPA for the UCMR, then validated by all the UCMR labs, and finally by all the labs nationwide that are currently using the method for PFC, for monitoring PFC for the health advisory. ASTM D7979, as mentioned, was developed primarily at EPA Region 5 with some collaboration between vendors, members of ASTM, and validation using PT samples. Contrary to ASTM's own rules, there was never an interlaboratory study or multi-lab study conducted on this method. The draft ISO method does have an interlab study. Both the EPA and ISO methods extract PFCs from water samples using solid phase extraction or SPE. The EPA method requires 250 ml sample extraction elutes and concentrates to 1 ml. The analytical range of the method is defined by this 250 to 1 concentration factor. The ISO method allows volumes ranging from 50 mL to 1,000 mL depending on the concentration of the samples. Since you must use the entire contents of the bottle and rinse the bottle, the ISO method assumes you know the concentration of analytes before sampling. The ASTM method is very different in that 5 mL of sample is collected in a 15 mL tube. At the laboratory, 5 mL of methanol is added and the sample is injected. There is no SPE. Instead, there is a 1-to-1 dilution as PFCs are co-solvated into the 50-50 methanol water mixture. Holding times for all the methods are very similar. And since the EPA 537 is expecting chlorinated samples, Trisma is added. EPA method 537 is a drinking water method. We know that it has been applied to thousands of drinking water matrices across the country. The ASTM method was developed specifically excluding drinking water with the intent for a rapid, cost-effective method for non-potable matrices. We have tested this method in wastewater effluents, influent surface water, and groundwater. The ISO method is the only one that actually has a multi-laboratory study where each lab ran the same matrix, validated using drinking water, river water, seawater, and wastewater. We must be careful here with the use of the word wastewater because for ISO, this usually means a clean secondary or tertiary effluent. Now for analytes. As mentioned earlier, method 537 well, as not mentioned earlier. Method 537 is similar to what most of us that are used to GCMS methods are accustomed to. 14 compounds plus 3 surrogates are extracted by SPE. The extract is concentrated to 1 ml, to which 3 internal standards are added, and the same sample extract is run by LCMS-MS. The ASTM method more closely resembles a GC-ECD method, where surrogates are added, the sample is extracted, except in this case, the extraction includes a miscible solvent, and then the extract is run by LCMS-MS. The ISO method uses a technique called isotope dilution, where a carbon-13 labeled isotope, one for each analyte, is added prior to extraction. The sample is extracted and concentrated, and concentration of the non-labeled isotope is calculated relative to the added labeled isotope. The ISO method does include or allow for an external standard calibration similar to the ASTM method. However, it is the intent of the ISO method that the external standard calibration be used for analytes for which there is no isotope, and more importantly, during method development as you optimize the recovery of each isotope and analyte. In other words, the external standard calibration is used to optimize the external standard calibration is used to optimize the internal standard calibration. EPA method 537 requires a force through the origin, and the other two do not. ISO refers to their calibration standard on checking for the goodness of fit, and this calibration standard contains various options. We don't necessarily know what the lab is going to use. Method 537 includes an asymmetry check. ASTM and ISO do not. All methods require separation of branched and linear isomers. This requirement is not related to a final calculation of branched and linear as total. Some of the calibration standards are not available pure. The separation requirement is to ensure a satisfactory calibration by making sure that impurities in the calibration standards are resolved. The result of the isomer separation requirement is longer chromatograms. ISO methods don't really discuss QC in the same way that US methods do. The QC is expected to be defined by the laboratory or possibly by the country that sets the regulation based on the ISO standard. So in that, ISO does not really define acceptance criteria based on an MRL standard. ISO does define acceptance criteria of internal standards and surrogates, and these criteria are very similar to the US methods. Note that ASTM, though written as an external standard calibration, does allow the surrogates to be used as an internal standard. The current QC acceptance criteria of 70 to 130% would still have to be met. ISO does not specify precision data. Instead, it refers to single lab and multiple lab precision from the interlab study. Other than that, the methods are essentially the same. Since ISO does not require an MRL, I have no data for that. You may recall that I stated that we don't modify method 537. However, in these examples, more compounds were added so that a more direct comparison with the ASTM method could be made. In looking at this data, keep in mind that the EPA method is a 250 times concentration factor and that the ASTM method is a 2 times dilution factor. MRLs are fairly equivalent, with the ASTM being a bit higher. The ASTM method was run on a fairly new instrument, and the EPA method on an older instrument. Lower MRLs for the ASTM method are possible on even newer, more sensitive instruments, but I did not include any of that data. This is percent recovery data. Again, I tried to pick compounds that were in all methods, but I missed some on the ISO. Assuming a 70 to 130% recovery requirement, all methods perform equally. The same group of compounds, its precision is about the same, and all methods meet a less than 30% criteria. Now I'm going to switch gears briefly and discuss some of the problems, as I see it, encountered with PFAS analysis. Mainly, the compounds are not listed in any regulation anywhere. There's a health advisory for drinking water, but no MCL and no promulgated method. There are no EPA-approved methods for RCRA or Clean Water or the Clean Water Act. This is causing a preponderance of lists and modifications of methods. In the absence of regulation or a set list, methods are being modified, but when methods are modified, you really don't know how or if the data can be compared. We know that EPA is working on a new method 537. Will that method be approved with an MCL established, or will labs continue to modify method 537? If drinking water methods by definition cannot be modified, what does modified method 537 even mean? How is it modified? Does each lab modify it equally, or is each lab running something different? Are labs separating the isomers, or are they compressing chromatography for faster results? Are they using different SPE media or no SPE media at all? Are they doing isotope dilution? And if so, what QC criteria is required in the method development and optimization for the isotopes recovery? Remember that LC-MS also includes liquid chromatography. It is not just mass spectrometry. All the peaks must be separated. Short-run methods may seem to work on standard solutions or reagent waters, but do they work on real matrices? The next two slides show some real data that was collected on shortened runs. Notice that the elution time of these peaks is clockwise 2 minutes, 3 minutes, and 4 minutes. For each set, there is a nicely shaped isotope paired with the analytical peak. You notice that there is other stuff eluting with the analyte peak. This other stuff was quantitated as the analyte, but it is not the analyte. The analytical peak should have the same shape or very near as its labeled isotope. Another example of quantitated, poorly resolved peaks. Notice in these examples, the time is all less than 5 minutes. The chromatogram on the top is ASTM D7979, and on the bottom is EPA method 537. Pictured on the right of each is a peak showing that these chromatograms fully resolve the linear and branched isomers. This separation is a good verification that the chromatography is suitable. Notice the full chromatograms. For the ASTM method, collected using an ultra-high pressure liquid chromatograph, the first peak elutes at about 3 minutes. All other peaks emerge at 4.5 to 12 minutes. Ultra-high pressure liquid chromatography is specifically designed for faster analyses. The EPA method was run using a lower cost, high pressure liquid chromatograph. The first peak elutes at about 6 minutes, and the run is finished in about 20 minutes. These are analytes and labeled isotopes with about the same shape and how they should look when you quantitate your samples. EPA requires that regulatory methods have an interlaboratory study. The ISO method does have an interlab study. However, ISO methods do not include quality control that is also required of EPA methods. EPA method 537 has been UCMR validated for its analyte list, but not for additional analytes, matrices, or lower detection limits. EPA is updating method 537. ASTM, for political reasons, broke its own rules and did not conduct an interlab study on D7979. That study is now underway. In addition, EPA, as mentioned earlier, has validated a similar method as SW846-8327. Some things to remember. LC-MS only sees what you are looking for. It is not like GC-MS methods where you can scan unknown peaks. High-resolution LC-MS is a way to identify and guess as to what other PFAS compounds may be in a water sample. But high-resolution methods only measure 1 or 2 masses. It's not a spectra like GC-MS. Therefore, you still need a standard to positively identify a compound. I say this because new method development needs to be able to find and rapidly adapt to changing analyte lists and lowering detection limits. In summary, we compared three methods: one direct inject method, one SPE internal standard calibration, and one SPE isotope dilution calibration. All methods have similar QC acceptance criteria, similar MRLs, and similar accuracy and precision. LCM-SMS after SPE or with co-solvation and direct injection has proven a powerful tool in identification and quantification of PFAS using a known list. Methods need to be standardized and modifications discouraged to ensure that data are comparable. Finally, a system needs to be in place that enables more rapid method development and acceptance. As chair of ASTM D19, editor of standard methods, and a U.S. representative to ISO, I represent consensus standard organizations that stand ready to assist in this challenge. Thank you very much.
Thank you very much, William. And now we're going to switch to our next presenter, who is Janice Willey, and she is a senior chemist with the NAVC Department of Defense Laboratory Quality and Accreditation Office. Janice, are you ready to go?
All right, can you hear me?
Yes.
All right, you got my slides? You can see them?
You're good.
All right, wonderful. Let's get going. All right, good afternoon. For the next 15 minutes, I'll go over a brief overview of the DoD's requirements and initiatives relative to PFAS sampling and analysis. As a federal government employee, I, of course, have a love of acronyms. So in order not to lose everyone in the alphabetical soup, I will try to define them during the presentation, but if you don't have to take any notes because when these presentations get released in the speaker notes, I've provided the acronyms definitions for you as well. So as stated, I'm a senior chemist for the Naval Sea Command's Laboratory Quality and Accreditation Office. And I'm also a representative for DoD's Environmental Data Quality Work Group, the EDQW. For those of you not familiar with the EDQW, this is a group comprised of representatives from the Air Force, Army, and Navy that have been tasked with providing the DoD recommendations for sampling, testing, and quality systems policies, as well as developing guidance documents. As you can imagine, this group is heavily involved in PFAS sampling and analysis issues and producing guidance documents and helping to address current and future needs relative to PFAS. One such guidance document the EDQW has developed is a document entitled Bottle Selection and Other Sampling Considerations when Sampling for PFAS, which can be found on the DENX website. This document was published in 2017. It recommends the use of high-density polyethylene bottles for sample collection of non-drinking water media and provides a list of materials to try to avoid using during sample collection, as well as those recommended for use. These recommendations were based on information gathered from previous PFAS sampling experience and input from laboratories and researchers. As you all know, what we know about PFAS is ever-changing, and as a result, this document is currently undergoing revision. It's being updated based on the current state of knowledge and will be in line with the recommendations made by the Interstate Technology and Regulatory Council, the ITRC, their PFAS documents that they're continuing to publish. It'll take a practical approach focusing on those sampling supplies and equipment that comes into direct contact with the samples, as well as those supplies that come into direct contact with the sampling equipment itself. As most of you are aware, the DoD's primary source of concern relative to PFAS is aqueous film-forming foam, or AFFF. My office, LQAO, has developed a protocol for sampling contained AFFF, such as that in trucks and hangars and drums. The current specification for AFFF used by the DoD is that it must not contain PFOA or PFAS at levels greater than 800 ppb. So these AFFF stocks will be evaluated to that standard. If they exceed these limits, they'll have to be replaced with AFFF stock that does meet the standard. In order for the new AFFF stocks not to be contaminated by the residue from these old stocks, the hangars and the trucks will have to undergo some method of cleaning. The Navy is currently conducting research to determine an appropriate cleaning procedure for these containers. With regard to analytical requirements for the DoD, any laboratory used to collect definitive PFAS data for environmental restoration projects, AFFF evaluation, and various other programs are required to be DoD ELAP accredited. The DoD's Environmental Laboratory Accreditation Program, ELAP, is an accreditation program which uses third-party ILAC signatory accreditation bodies to assess laboratories. The accreditation standard they assess to is based on the ISO 17025 2005 and the NELAC Institute TNI 2009 standard. The DoD standard, the DOE Quality Systems Manual for Environmental Laboratories, or QSM, currently is revision 5.1.1, includes all of the requirements in ISO 17025. Therefore, a laboratory compliant with the QSM is compliant with ISO 17025-2005 standard. DoD ELAP accreditation is a method media analyte specific accreditation, not a method media specific accreditation like some other accreditation programs. Okay. A copy of the QSM can be found on the DENX website. The DoD ELAP accredited laboratories are accredited to EPA method 537 for PFAS in drinking water, and for all other media and method identified as PFAS by LCMS-MS, compliant with QSM 5.1, Table B15 is used for accreditation. The use of EPA method 537 for drinking water and PFAS by LCMS-MS compliant with QSM 5.1 Table B15 for other media is required by many DoD policies. The PFAS specific requirements for analysis of other media, as indicated by the method designation, are contained in Appendix B, specifically Table B15 of the QSM. These requirements were based on input from researchers, instrument manufacturers, EPA method, laboratories, commercial laboratories, and standards and PT providers. The table includes sample preparation and analytical requirements based on concentration levels and media type. How can you tell if a laboratory meets the requirements? Only laboratories with DoD ELAP with a DoD ELAP scope of accreditation listing PFAS by LCMS-MS compliant with QSM 5.1 Table B15 are documented as meeting these requirements. I want to make a few things clear about Table B15. Table B15 was created due to the lack of a published multi-laboratory validated method, such as an SW846 EPA method. It is not a method and is not applicable to drinking water analysis. Does the DoD want a published method? Absolutely. This Table B15 is merely a stopgap approach to address some of our concerns and try to make our data much more comparable from laboratory to laboratory. Over the last few years, the EDQW has collaborated with researchers, standards providers, and instrument manufacturers and EPA laboratories to help provide DoD ELAP laboratories with the most recent advances and knowledge relating to PFAS analysis through workshops. As a result, we've been able to greatly increase the number of laboratories that are capable of performing PFAS analysis to our requirements. So this slide here, slide 7, gives you a list of, as of October 3rd, the DoD accredited laboratories for PFAS analysis. We had on October 3rd, we had 12 laboratories accredited for drinking water by method EPA 537. 15 were accredited for aqueous media, 14 for solid media, 3 laboratories for tissue media, and 3 for AFFF media. And all those last 4 are under the PFAS by LCMS-MS method. The reason why I stress this is as of October 3rd, on October 3rd, is that accreditation is ever changing. It's not a static thing for us. And so if you want to see who is currently accredited, I'd advise you to go to the website provided, link provided, and you can get the most current information on that. I have on the slide that those media are accredited to PFAS by LCMS compliant with QSM 5.1 Table B15, not EPA method, EPA 537 mod. I make this distinction because there are still laboratories within our program that get accredited to EPA method EPA 537 mod method under their scope for use for other clients. A method specified as EPA 537 mod has not been determined by the DoD ELAP accreditation process as being compliant with Table B15 requirements, therefore cannot be viewed as equivalent to methods identified as such. While laboratories may claim these methods are compliant with Table B15, the DoD does not recognize any method as compliant until it is included in their DoD ELAP scope of accreditation as the PFAS by LCMS compliant with QSM 5.1 Table B15 method. And therefore, any methods that aren't identified as such will not be used to collect definitive data for the DoD. You can find that's the current status of our requirements in a nutshell for the DoD ELAP. But what does the future hold? We are currently engaged in two substantial tasks related to DoD ELAP PFAS requirements. First, the QSM is currently undergoing revision based on our current state of PFAS knowledge. We are incorporating QSM frequently asked question answers and knowledge gained from laboratory assessments, recent publications, and laboratory and project feedback, as well as other lessons learned. This update to Table B15 will be included in QSM 5.2, which is due to be published in early 2019. In addition, the EDQW is performing a laboratory control study, LCS study, for PFAS in solid and aqueous media. This study will use data provided by the DoD ELAP accredited laboratories to generate LCS and extracted internal standard performance criteria. These criteria will be included in Appendix C of the next version of the QSM, and laboratories will be required to meet the criteria by the updated requirements of Table B15. So both the immediate changes we're making to the overall QSM, as well as specific to inclusion of a laboratory control sample study, are going to be included in the next revision of the QSM 5.2. In addition to these updates, NAVCL-QAO and the EDQW are collaborating, as Chris said, with the EPA to develop the isotope dilution method that allows for compliance to the DoD QSM requirements found in Table B15. We are also working with the Firefighting Foam Coalition to develop an isotope dilution method for AFFF media. Analysis of a product such as AFFF represents some difficult challenges not typically encountered in the analysis of environmental media. The method we are evaluating will be able to overcome these challenges, allowing for a much lower limit of quantitation to be achieved for approximately 31 PFAS in AFFF and AFFF mixtures. So I've talked about PFAS sampling and analysis. What about the data generated for those efforts? Is it fully understood and how to properly evaluate this data? Are the advantages and limitations of various evolving methods understood? From the EDQW's outreach efforts, there appears to be a need for some guidance on data review and validation, as well as understanding evolving methodologies. As a result, we are collaborating with the EPA to develop PFAS data review technical brief, as well as the EDQW is using this document as a basis to develop a DoD-specific PFAS data review guidance that is tailored to the DoD ELAP requirements. Following the creation of this document, the EDQW will develop guidelines for PFAS data validation. And lastly, the EDQW is developing a white paper to help DoD project teams understand one of the emerging PFAS methodologies, total oxidizable precursor assay, or TOP assay. What I've presented here today are some of DoD's efforts in the realm of PFAS sampling analysis. In addition, the DoD funds research and participates in many other PFAS efforts dealing with other aspects of the PFAS issue, such as remediation techniques, advancing the understanding of PFAS, state and transport, and toxicity. On this slide, I've provided you with links to 3 of these programs. I encourage all of you to take a look at these websites as they can provide a wealth of PFAS information. With that, I am concluding my presentation, and I thank you for your attention.
Great. Thank you very much, Janice. And so at this point, I just want to remind everybody to please type in your questions. So Janice was the last presenter for today's webinar, and we do have a couple of questions that have come in already. So I'll start with one that is about the asking what the typical analysis fee is for using EPA method 537. So maybe Brandon or William, you might be able to provide an answer to that question.
Depends on the list, about $300 to $500.
Okay, great. And is that normal for you too, Brandon, there in New Hampshire? Is that typical fee?
For method 537, we've seen pricing from $175 to a few $100s. It really depends on how you go about obtaining lab services. If you develop an RFP as a state or as a water system with a large quantity of samples and competitively bid it, you of course making sure you have the right specifications, requirements in the request for proposals, you will get some very good pricing. But if you're just showing up at a lab and asking for a single analysis, the pricing would be much higher.
Okay, great.
I'm including list price. So.
Okay, thank you, William and Brandon. So the next question, and this is kind of a long one, so bear with me. We've heard about using expanded scope of PFAS measurements to fingerprint potential sources of contamination. It seems like this person is asking if there is a guide to correlations between what you might find and where, therefore, to look, such as patterns of PFAS and known uses.
Yeah, in New Hampshire, we've developed a list of industry codes of industries that potentially could use PFAS. And as far as fingerprinting goes, we just, we know from the nature of the industries which might have used historically more PFOA versus PFOS. And when we have waste sites that overlap one another, while a lot of them will have common contaminants, sometimes, PFHXA might be associated with one plume, but not in the source area of another. And so you can start trying to figure out the extents of plumes and where the overlap occurs and where it's not occurring.
Great. Thank you, Brandon. And another question, what kind of matrix interferences have been seen in drinking water samples? Are specific water quality issues known to cause problems? So maybe again, this might be for Brandon or William or Chris and Janice. Please chime in if you'd like.
I can just say from New Hampshire's experience, we've done split sample studies using in-house isotope dilution methods for 4 different commercial labs, as well as method 537, isotope dilutions correcting for matrix interference. And it's all been on drinking water samples, either public or private wells. And in our analysis of drinking water samples, we haven't seen a lot of matrix interference, but I understand it can be a substantial issue, which is why some chemists prefer isotope dilution, especially for other media. And I'll defer to the chemist to get into that a little more.
But there's not really any. I mean, if you do the chromatography right, there's not really any matrix interferences. I mean, there could be some compounds that elute that could cause suppression or enhancement of the signal, and that's why LCMS people like isotope dilution. But in a drinking water sample, that's not likely to be there. A well water, possibly, a river water, possibly. But I mean, LCMS-MS is I mean, a really pretty robust technique.
Great, thank you. So next question looks like it's for Chris at EPA ORD. What SPE phases are being looked at to target shorter chain PFAS compounds?
I'd have to get back to you on that.
Okay, no problem. We can provide an answer to that question after the webinar for the participants who registered. All right, and let's see. We have another question that is, what's the purpose of forcing through origin in calibration for method 537?
This is Chris, and again, I can contact Jody Shoemaker, the developer of that method, and provide an answer for that.
Yeah, I'm not going to answer to the purpose. I just mentioned that it's there. So.
Okay, no problem. Thank you. We'll follow up on that one as well. And I don't know if we have any other questions at this time. Maybe, Brandon, maybe I can switch back to you for a minute. There's one person who wanted to see your slide again at the very end, and I believe it was on topic 6 of the lab primer on sample collection procedures. So I'm not sure if that person had a specific question, or Brandon, you could try to pull that up. And let me just remind everybody that the ASWA lab testing primer will be published by the end of this week, so look for that coming out. And we want to thank Brandon for his helping with the development of that and our PFAS work group. I can also remind everybody that the slides and the recording of the webinar will be available on ASWA's website after the webinar in the next few days. So look for it there. And I'm going to go back to my questions here. So just look for the webinar recording there. And please type in your questions if you have them. Okay, let's see, there's one more here. It says, good method for short chain, I'm not sure what this means, J Chrome A volume 1345. I think it's referencing some type of document there. Let's see, one other question came in. Building an existing basic laboratory already exists. Is it only for EPA method 537? So I'm not sure exactly what that question is asking. Maybe, yeah.
Can you read it again?
It says building an existing basic laboratory. It looks like there might be a word missing. It says they already exist. Is it only for the EPA 537 method? So I'm not sure if that's referring to additional methods that are being developed. Okay. Let's see, I have another question here. Is instrument modification always required to avoid contamination?
Say that again.
It says, is instrument modification always required to avoid contamination?
Yes, you have to remove all Teflon in the instrument. So most LCs or LCMSs come with Teflon tubing, like for instance the line that takes the mobile phase down to the pump, and the instrument manufacturer should do this, but all that should be changed to something else. Perhaps PEEK is what a lot of people are using, and also a lot of the LCMS manufacturers have what's called a degasser, and that's usually a Teflon or has Teflon fitting in there, so you can't use that either. So you'd have to degas your solvents old school. But yes, you have to modify your instrument. Other than that, there's no modification.
Great, thank you. And I have another question going back to Brandon's presentation about your comments on the acid versus salt results coming back from laboratories. And do you have some more recommendations for states on how the salts can be converted to acids, or whether they might need to retest some of their samples?
Sure, and I know the chemist on the call probably can answer better than I, but it's my understanding that the labs measure the anion form and can convert it to the salt or acid. And so if you did get historic results in one form, it can be converted to the form that you're interested in, again, which is probably the acid form, because that's what the health advisories are based on. And I can't stress enough the importance of everyone getting on the same page on this issue, so that when CAS numbers are used and lab reports have chemical names written, that we start seeing the same thing, and that the chemical names match the CAS number. And a lot of times the concentration will be substantially the same if you're in the acid or salt form, but I know of one national lab that does a lot of work that reports PFAS in the salt and a potassium salt form, and that alters the result by 8% when compared to the acid form. So it's just from a data integrity standpoint, it makes sense to get it straight, and there's really no problem with everyone getting on the same page. It's just everyone needs to agree to one way to report these compounds so that our databases and reports and everything match one another.
Yeah.
Right,
so
and if you go ahead.
Go ahead.
Well, if you buy your standards and they come in the salt form, you need to take into account that the concentration might not be reported correctly. So you have to, if it comes as the potassium salt, you have to take into account that there's potassium there and recalculate your concentration based on the form of the anion, not the potassium. I don't know if that made sense, but
yeah. So one of the big producers of standards for this analysis is Wellington, and a lot of laboratories utilize their standards, and their certificates of analysis for their standards include both the salt and the acid concentrate, or the anion concentration for the sulfonates. And so that's where there's been a lot of hiccup. Even when a laboratory identifies for their CAS number the acid, that's why the data review is so critical, because a lot of laboratories we have found have incorrectly calculated the calibration, because they have based their concentrations off of the salt versus the anion concentration from the certificate of analysis of the standard that they use to make their calibration standards. So that's one of the reasons why, the data review becomes super critical with these analyses, is that, there is room, it seems to be there's a little bit more room for error in some of the calculations because of how the standards are purchased, and what the concentrations could be in the form of the salt or the acid, like we said.
Great, thank you. And I have another question about the common portion of PFAS compounds, but I think it's related to sort of screening, is there a way to screen for whether PFAS are present before determining what exact compound is there?
This is Chris, and that would be something along the lines of the total oxidizable precursor assay.
Yeah, we've been trying to develop one that does basically TOF, kind of like a TOX, but the sensitivity is super low, so it doesn't get you down to the nanogram per liter anywhere close. And we still have questions about whether it's even oxidized. So there's companies out there selling it, but so far we've been unable to validate it.
And when you say TOF, you mean total organic fluorine? Is that what you're
saying? If you're familiar with like TOC or total organic halogen methods, where they combust and then you measure a product, this method says it combusts it and then it measures fluoride by ion chromatography. However, these compounds are so resistant to combustion, the question is, do they really combust? And do you create HF and do you measure it? So there's lots of validation required, but there's people mainly in Europe and some other instrument manufacturers that are selling this. But the detection limits are like, go ahead.
No, go ahead.
The detection limits are high. I mean, they're like, I think the last data we saw, this was at ASTM, was probably about 100 ppb, and we still haven't seen them provide data for PFAS compounds.
Yeah, and some of the same concerns really apply to the top assay as well. If you're keeping up with, what's kind of out there relative to PFAS, we used to think that there was 1,000. Now people are thinking there's anywhere from 3,000 to 5,000 different PFAS that exist out there. And the top assay, while we have some standards that can help validate some of the precursors that could possibly be there and be transitioned to end product, we do not have standards for any and all and every single PFAS that's out there. So we got to use the term total loosely, because the methods that people have created out there for top assay, again, it's now a published method, can greatly vary in their ability to account for all of the PFAS that are out there.
And you can do high res, but one of the issues with high res is you're not going to see the longer chains, because high res is basically you're sucking water right out of a bottle. So anything that's stuck to the sides, you're not going to see. Plus, you don't know. You can get an idea that there's a peak, or that there's a fluorinated compound based on its mass. But because LCMS-MS really only looks for one mass, you're just kind of guessing that that's the peak that it is. And you can't really identify it conclusively unless you have a standard, and there's no standards for most of these compounds. So you can do a high-risk screen and get an idea, but it's just an idea.
Great, thank you so much. And just one more question for Janice. Do you have an estimated time frame for when your data review, technical brief, and data validation guidelines will be available?
Okay, so for the EPA one, Chris, that's I think more of a question for Chris.
Okay, right,
that one.
And DOD technical brief.
Right,
yeah.
Right.
First on the brief, Janice just sent me the last version. I'm working on it this afternoon, so hopefully we'll get that through the clearance process within ORD and get that moving, and hopefully get this out for the public within the next month.
Excellent. And I suspect we're going to be we should have our DoD specific guidance out by, I would say, the beginning of December. The validation guidelines are going to take a little bit longer because they are extensive and they're going to be included. We have published general validation guidelines for SW846 methods and DoD work analysis done for DoD sites. That is actually on that DENIX website as well, and anybody can download it. We are generating specific validation guides for all types of analyses for the work that's done for DoD, including the PFAS. I suspect the PFAS validation guidelines, specific guidelines, will be released probably more towards next summer.
Okay, great. Thank you so much. And with that, we have gone past our time. So I want to thank all of you presenters for sharing all this great information with us today, and thank the audience for joining us. Look for the webinar recording and the presentation slides on our website at www.asra.org in the next few days, and I hope everybody has a great afternoon. And with that, we will conclude the webinar.